how about now? Oh, now I have a mic input. Okay, how about does
How
this
about
work?
now?
Oh, now I have a mic input. Okay, how about does
How
this
about
work?
now?
Awesome. All right, OBS is great. Okay, let's adjust this title. Okay, now theoretically, if I go to my channel, go here. Okay, now theoretically, if I go to my channel, awesome, it worked. Okay, I'm going to assume it sounds perfectly fine. Then I will have the chat open on phone so I can read it. And ideally, this should go splendidly. It's on my phone. Testing audio. Please? It's not grainy, right? I'm begging you. I'm going to say a very long sentence, so hopefully all of it goes through without... Okay, great. Yay, audio good. Give me a second. Let me get my laptop out so I can read it better, and it's not on a very small phone. Stupid show on the road. 17 minutes later than I was supposed to get. Laptop has battery, right? There's 6 people here already? Damn. Why? Why are there so many of you? Okay. Everyone's here, hopefully. I see 5, so somebody left, but I do not care. They can come back and do it later, right? Yeah. Okay. Time to jump right in. Practice midterm number 1. This should look familiar to you because you probably did it before, but we're just going to review it. And I'm going to draw all over it, and hopefully it looks good. And I'm not terrible at art. Okay. Lewis structure for NH3. N is probably the center one. And then we just draw the hydrogens. Hydrogen. And if I pull up a periodic table, we also have to keep in mind the formal charge. N has a formal charge of 5. So we have 1, 2, 3, and then 4, 5. So this is happy. And if we look at boron, which is here, it has 3. So unlike N, which has the lone electrons, boron is going to be perfectly happy just having the 3 Fs attached to it. Also, don't forget that these Fs have lone electrons, or not like the hydrogen. So it should look like this. And if I look at the answer key, hopefully I did not get that horrendously wrong, which I did not. Hooray. Now we look at electron pair geometry. So electron pair, as opposed to molecular geometry, is we also take into account the electrons. So this is 1, 2, 3, 4. So this would be tetrahedral. And this one has only 3, so this would be trigonal planar. I think. Wait, am I tripping? No. Yeah. This one would also be trigonal plane again because it has the B, and then this one would be trigonal pyramidal. The pyramidal? Or is it? I mean, autocorrect seems to think that's right. It's trigonal pyramidal because normally tetrahedral would look like this, kind of. The dotted line is like behind it, right? So imagine it's like kind of like I can't. It's a tetrahedral shape, right? But without the top part, because it's only electrons here, all you would have is this, which makes it a pyramid. If that makes any sense. Yeah. And then the formal charge in the central atom we went over. Formal charge here. Wait, formal charge. Oh, yeah, 0. They're both perfectly happy as they are, so their formal charge is 0. Lewis structure of NH3BF3. Why would these two molecules tend to react? So the Lewis structure of the product would be, I believe, like so. And that's because the boron, even though it's perfectly happy having 3, it still has space in its octet. And same thing for nitrogen, where nitrogen, even though it's perfectly happy having 5, it can still donate those 2 to like share it, so that they can still make the bond together. So the reason both central atoms have space in their octets to allow for another bond, and nitrogen can share its lone electrons by with the empty slot in boron's octet. That's that. And if I look at the reasoning, yeah, the boron now attains an octet. So pretty much they will both be happy, despite the fact both of them have charges on them. They will have full octet, so they will be happy. Okay. For this, we know that both of them are at the same room temperature, and they initially start at the same volume. So pretty much it's asking on average which sample of gas molecules is traveling at a greater velocity. The answer is NH3, not because it's not both are the same, because if you remember that at a specific temperature, kinetic energy of things are going to be the same, but not the velocity. So remember that kinetic energy is 1/2 mv squared. So if you were to set those two equal to each other, their mass, because m is mass and then v is velocity, their masses, individual masses, are different, so therefore their velocities also must be different. And nitrogen weighs more than boron, BF3, or weighs less than BF3, sorry. So it would probably have more distributed in a velocity. So this one would probably be going faster. And then you do that calculation here by setting the kinetic energies of both equal to each other. So it's 1/2 mv squared equals 1/2 mv squared. V squared 1/2 of what's its face? Oh, this is V1 for NH3 and this is V2 for BF3. And then so molar mass NH3 because I'm too lazy to type to actually do the calculation. 17.031 half, and then BF3 molar mass 67.81. Those cancel, and now we're looking for like the ratio between the two. So we want V1 squared over V2 or V2 squared is equal to 67.81 divided by 0.031, and then you take the square root both sides to get the ratio between V1 over V2. And where's my calculator? Where did I find this? Do you have a different practice midterm? I mean, I just had this in my files. If I feel like, is this not the official one? Is this like the practice one? Check. Yeah, this is last year's, so it's a year behind. I can go over this one if you want, but I was originally planning on doing this one and then this one after, because this one's a little harder than this one was, because this one's a little simpler, so it's easier for me to go over this one. I can quickly speed run through this one after, where I just go through the answer key, but this one goes first, because this one less people have seen, so it's more likely that it'll be of more help to them than reviewing the other one. Yeah. Okay. Calculator 67.81 divided by 17.031, and take the square root of that. It's like 1.99, which means V1 is like basically 2 times faster, so it would cover double the distance. So NH3 would be, they'd meet up around there. And then after the reaction is complete, what happens to the pressure in the apparatus? Wait, the pressure in the apparatus, would it decrease? Why? Yeah, it decreases. I think it decreases purely because, like, despite the fact that there's so when everything goes in, there's a lot of molecules like bumping around. I guess it like all evens out, because before, I guess how I'm reasoning it right now is that when those tubes are open, I guess this thing's volume is also increased by this area and this area. So eventually this stuff would reach here, and eventually that stuff would reach there. And we all know PV equals center T. If pressure goes down, then volume must go up to compensate. So volume increase, overall volume increases when these two gaps go in. So I presume it'd be this. Although that's probably horrendously flawed reasoning, but I think that should be fine. Okay, sulfur oxide. So let's just start with sulfur, oxygen. Okay, we probably want to satisfy oxygen because it's the easier of the two, and I know oxygen's formal charge is like 6, I think, so it's gonna be happy with a double bond and like that. And now we just fix up sulfur. So if we look at periodic table, sulfur has 6 as well. It's the same as oxygen, so I think it would be perfectly happy if it looked like this, like that. Yep. And then draw two Lewis dot structures, including Vesper for SO2s, one that obeys octet and one that minimizes formal charge. So the one that minimizes formal charge means that the sulfur would have to double bond twice to the oxygens. I think. Wait, one that obeys the octet. Oh, so if I wanted this to be happy with formal charge, it'd have an extra thingy. So this disobeys the octet rule. And then one that does obey the octet rule would look more like this, I think. That is terrible, O. And then I think it would be like would it be this? Wait, one. Yeah, it would look like that. And then the overall charge across the whole thing is like minus one. Minus one, I think. Yeah, but it's minus plus. Ugh, annoying. Because they want it the other way. So it's this is minus because it has slightly over because it's 1, 2, 3, 4, or slightly under. Sorry, so it's 1, 2, 3, 4, 5. Blah blah. Wait. Plus. Yeah, plus. Sorry, because it's under. It has less electrons than its formal charge, and this has more. So this would be the minus. And then its alternate variant is just it flipped. So S double bond O. Okay. Given the structures and experimental data, which model is more valid? Okay. Well, the experimental data says that the bond length here for sulfur dioxide is like slightly longer than 143, despite them both having double bonds. So I presume it'd be a little funky and not really obey the octet rule because if we actually look at its behavior, which is that it's slightly longer than just the sulfur monoxide double bond, if it were to do this, it would actually be a little shorter, right? Because it's swapping itself between a double and a no. I think double bonds are shorter than singles, right? I'm gonna double check that. Double bonds shorter. Yeah, it is shorter. Yeah. So if okay, I'm not entirely sure because the answer key says you minimize formal charge, which implies this one's correct. Actually, so if it has double bond like O2, so S2 probably has two double bonds as well. So it's literally just saying that because of the fact that sulfur oxide or sulfur monoxide on its own is stable, that sulfur dioxide with the double bond would also be stable. I don't really understand the reasoning behind that either because I thought this here with the double bond, the bond length being slightly longer and it having a double and a single, so it's this thingy right here, the net 1.5 bonds, so it's slightly longer than um sulfur monoxide, which is shown here. It still says this is the right answer. I don't know why. Huh. I mean, it says other answers that are logical are accepted, so no problem's just a little strange. Oh well. Okay. This one, I think this is just PVNRT. No. Yeah. So after the gas is heated to 600 Kelvin, so um, it would be like up here, right? Because they heated it up, and then can I get like a slight? Yay! I'm an artist, guys. Look, I'm so good. Yeah. So it would be up there because we heated it. So that's firstly. The position of the piston, that would be like up here because it started at 300, so we would expect that the piston like doubles in area. Or that's not doubles. I need to draw it higher. You'd expect the piston is up there. Up the reading. Big arrows mean moving faster. Small arrows mean moving slower. Probably. Wait, 1, 2, 3, 4, 5, 6, 7, 8. And then the arrows on these be like longer, I think, because they have more temperature, which means higher kinetic energy, right? So they're moving faster. Yada yada. God, I suck at drawing arrows. And then the pressure, however, would stay the same. Because volume's able to move. So the volume moves and the pressure stays the same. So nothing really happens to the pressure. So at 600K, the pressure inside the cylinder is equal to. That's because PV equals nRT. We increased T and we're letting V change as well. So V is just gonna change a little bit while P stays the same. Yeah, equal to. Use a motion to explain the value of the pressure inside the cylinder after the sample stabilizes at 600K. So pretty much what happens is that motions and collisions, is that literally what I think it is? Okay. So pressure is determined by the energy of and the frequency of the collisions that occur. Because the sample was heated, the molecules inside are moving faster and have a greater kinetic energy. Therefore, the molecules will collide with one another and also the piston at a higher frequency, and thus is able to push the piston backward. Piston to double the volume to correspond to the doubling in temperature. If we consider the ideal gas law, an increase in temperature is proportional to the increase in volume, and therefore we can assume that the volume also doubled. Okay, so that's a very long explanation, but pretty much that. What is the volume of the gas at 600K? Oh my god. 1 liter. Because PV or actually you could just do Le Chatelier principle, I think, where it's like if the proportional, it should be like P1 is equal to P2 T2. I think this is right. Yeah, because if this doubles, this has to double. Yeah. So P1 is 300, T2 is 600. So it's going to be, oh, P1 is also 1. So 1 over 300 is equal to P2 over 600. P2 equals 2 ATM. Or P2. Oh, volume. Sorry. Volume. Just messed up. Horrendous there. Volume is 500. And V2 equals 1 liter. Because 500 milliliters times 2 is 1,000 milliliters, and 1,000 milliliters equals 1 liter. Yeah. Oh, bonding. Great. Why are sugar and Kevlar not liquids at room temperature? So if we think in terms of intermolecular forces, if they bond together very well, then they are probably not going to want to be liquid. This is more of like a 1AL concept, to be honest. So, sugar and Kevlar aren't liquids due to having large dipoles, large LDFs because of their size. Because this is a polymer, and this is like a crystal, right? So it's big compared to the smaller H2O. So it'll have a larger London dispersion force and large amounts of hydrogen bonding. Because they have intermolecular forces, they are more likely to prefer to hold its shape and also, I guess, remain solid. I don't know how to like explain this. Yeah. The combination being large London dispersion forces, and strong hydrogen bonding means that they are solid. So, remain solid. And then a good comparison to this is water. So, in contrast, water is a liquid at room temperature, as despite the fact that water can hydrogen bond, it does not have large LDFs nor a strong dipole. Yeah. And why is sugar brittle and Kevlar flexible? This is definitely a 1AL concept. So sugar is brittle because its shape as a molecule would make it so that its overall construction, so like how it's more like Legos, where you're putting a bunch of Legos together, so it would like break apart, right? So it'd be brittle because these aren't long and like bendable as Kevlar is, because Kevlar is a really long chain. It's a polymer. right? And because it's long, um it can kind of, I guess, bend. Yeah. So pretty much what we covered in 1AL is that polymers, depending on how they bond, are able to resist certain like stresses applied to it. So I think flexibility was, it had to do with like, I guess, bonding. I think it had to do with like how well it can bond to itself. So Kevlar can hydrogen bond to itself very well, so it's gonna be able to like bounce back to its original shape. It's pretty flexible. So its overall construction would shear as it does not have the long, quote, bendable molecule makeup or structure that allows Kevlar to be flexible. But look at their explanation. Yeah. A crystal of sucrose molecules will be held together by hydrogen bonding. When pressure is applied, the crystal can break between the molecules, and they're H bonded all along the chain. So pretty much, they said it a lot more eloquently than I did, where I'm saying its shape as a molecule, which is like it being a ball. It'd kind of be like Legos, where you're just stacking them onto each other, right? So it'd break apart. As opposed to Kevlar, which is like a long, think of it as like fabric versus Legos. You can bend fabric because it's made out of a bunch of really long strings. You can't really snap fabric in half, right? But if you had like a Lego thing, you can snap that in half because it's not made out of really big long chains. It's made out of small, teeny, tiny plastic bricks. So there's that. Oh boy, multiple choice. A lot easier on me. Okay. Suppose you have a mixture of magnesium chloride and silicon dioxide. How can you separate one from the other? Um okay, this is hard because I feel like you would need, I want to guess either this one. I want to say this one. I might be wrong. Am I right? Oh, I am right. Okay. I guessed that one because MgCl2 is extremely similar to NaCl because Mg is right next to it. NaCl is a salt, so this is an ionic solid. So if you put it in water, it's gonna break apart. So if you, I don't know really how to explain this. Water is like the universal solvent, right? So it's very good at ripping apart ionic substances like MgCl2. So most of the time, if it's an ionic substance, it will have something from the first two, which is the alkali metals and the alkaline earth metals, and something from this side of the periodic table, which is like lanthanides. Is that what that is? Lanthanides? Yeah. All right, this should probably show up. No, it'd be reactive metals. Lanthanoids is these. Okay. Number of different molecules at the formula C2H6O. Oh boy. So let's first draw out the C2H6. I guess you can slap on an oxygen. Would it be like an OH group? Or would it be that you put the OH in the middle here? I feel like it'd just be one if you just pop the O in there. So if I were to like throw an oxygen here, that's a terrible low. Yeah, that's it. I want to say that. No. What's the other one then? Wait. Oh, okay. So I was right that you can add it as an alcohol group. Just the only problem is, like, yes, it considers the oxygen here and not, like, if you can throw it up here or whatever. I think that has to do something with the electron geometry, but it's 2 because you you can add the oxygen as, like, an alcohol group and not on it, and also on its own, I guess. Okay, highest effective nuclear charge. Where's my tabs? Effective nuclear charge. I would assume it would be here. Let me see if okay, it is fluorine. Because fluorine is the most electronegative, which is all the way up here. So I'd assume it have the highest nuclear charge because it really like wants. But there's yeah, 3.98 for its electronegativity. It's really big. Yeah. Oh my god, I can't do this. My hand-eye coordination. Most polar bond. Again, bonds with fluorine are gonna be like very weird because it is extremely selfish. So I'd assume it'd be LIF because of their difference in polarity. Yeah, because fluorine is extremely negative. So most of the time, fluorine, when it's bonding with something, it's gonna be extremely polar of a bond. And then liquid at room temperature. I think this is just the same problem as this again. So you want to look for something that is really weak intermolecular bonds. So I think MO is where's MO? My bond. Oh, it's here. That is a metal. So I would assume it'd be like a bunch of them together. So I don't think it can be this. Calcium oxide is I think is that I know it's dipole dipole. CH4 is nonpolar, but this is going to be a gas because CH4 is methane. This is ethanol, so this might be liquid. This I'm not entirely sure. I feel like this might be solid because it has dipole. And then GaAs is also another one. I think that's gallium and arsenic together. Ga is gallium. Yeah, it's gallium and arsenic together, which are both. Gallium is a metal, and then arsenic is a metalloid. So I would assume it would be. Is it ethanol? Yeah, it is ethanol. Yeah. So this is tricky because you're gonna have to guess a little bit. You also have to keep note where they are in the periodic table to know what they are. So I don't think they tell us this, but just generally stuff here and like the bottom left here are metal. These are also metal, and these are gaseous. So just firstly look at their intermolecular forces and then go from there. Largest bond angle. So if we go through, this is, I believe, bent. So this is like 109.5. This is, I believe, trigonal planar, which is, no, that's NH3 is trigonal pyramidal, which is, I think, is that 109.5 or 104? I don't remember. H2S is, uh, that is 1, 2, 3, 4, 5, 6. So is that tetrahedral? I think that's bent as well. Yeah, I think this is also bent. And then CH2O would be yeah.
Let me draw it CH2O. So I think it's C and then. And is it just like O and then H? Largest bond angle. Entirely sure how to draw that. I'm like bugging out right now. My head hurts. CH2O. Oh, it just attaches to the carbon, I guess. Is that trigonal planar then? I think that is trigonal planar. If I look, yeah, trigonal planar. So it's this one. That's the longest. Largest bond angle. Because this is CH4, which is tetrahedral. This is also tetrahedral, or its electron geometry is tetrahedral. This is also, I think it's bent, but its electron geometry is tetrahedral as well, because it has 2 lone pairs on the oxygen. This has 1 lone pair. This has 2 lone pairs on the sulfur, I think. Yeah. Molecules in no dipole moment. So just look for something that's non-polar. O3 is polar. I think SO2 is also polar. Carbon monoxide is definitely polar. Cl2 is also polar, so I presume it'd be this. Yeah. Lowest boiling point, again, look for stuff with the weakest intermolecular bonds. NH3 can H bond to itself, H2O can H bond, PbCl2 can, it has an extremely strong dipole because it's Pb, which is lead. Where's lead? Pb. Wait, where is lead? Am I here? Yeah. Also, lead is extremely heavy, so I would assume it's also gonna have a terribly high boiling point. And then HF is very I think is that hydrofluoric acid? I think so. It has H bonds as well because hydrogen bonds are FON, so I think it can also H bond to itself. So I would assume it would be this because it has the lowest intermolecular forces. Yeah. And then not soluble in water. Just look for stuff that isn't ionic. So NaNO3 is sodium and then nitrate, I think, because it's NO3 minus. That is a very common ion. MgCl2, again, covered earlier. It's soluble. Skipping over this because I know this is the answer. NO3 is it can hydrogen bond with water, and ethanol is also able to hydrogen bond with water. So I'd assume it would be this because it is a metal. Most ideal gas. Oh boy, this is the stupid one that I had to look at the table for. I think it was like here, ideal gas. Yeah, an ideal gas would be at an extremely high temperature and an extremely high pressure. So we look for something at high temperature and high pressure, and also what is mimicking an ideal gas the most. So helium versus argon. I think it was helium because it's lighter. Yeah. I don't think they're testing us on this because they didn't teach us to us this year, so I think we're safe. But we can probably ignore this one. It's boiling point. Pretty much opposite of this. Look for something with the strongest intermolecular forces. Xenon's a noble gas, so it's not really gonna want to do anything with itself. Same thing with helium. carbon dioxide is nonpolar. N2 is nonpolar. HF is polar and can also hydrogen bond, but I think this has a larger dipole, so I think it's CO. I think it's H2O. So I think it's that. Yeah. So despite the fact both of them can hydrogen bond, H2O can hydrogen bond more because it has two hydrogens firstly, and also it has a bigger dipole because the molecule's bigger. And then the best reason for my choice in question 11 is it's a mix of both B and A. I think it was mainly B though, because I eliminated like 1, 2, 3, 4 answer choices. So it's B. Which of these ions is least likely to form? So Ba2 plus. That looks like a noble gas. That's good. And then P3 minus gains 3. Looks like a noble gas. That's good. And C4 minus. That will also look like a normal gas. That's good. So Cl3 minus is definitely not going to look like one. It's going to go past it and it'll look more like calcium, which is not, it's not happy with itself, so it's that one. Yeah. Okay, for the questions below, circle all that apply. Assumptions that are made for an ideal gas. I think it's this one. Because we're assuming the collisions are inelastic and they're also like non-bend. Yeah, so it's like both of these two mixed together. I'm not sure. Yeah, it's definitely not D. It's definitely not E either. Yeah. Ideal gas, we just assume like the average mass for all the particles, and then proceed that they heat up when they collide. I think that has something to do with like their attraction to each other. And then E, again, all we're looking at is average kinetic energy and not individual kinetic energy for the particles. Yeah. Statements that must be true about a 22.4 container with nitrogen gas at STP. So standard temperature and pressure means 1 atmosphere and I think room temperature. So we know that it's guaranteed to be 1 atmosphere. The gas itself, we're not sure about the temperature because it says I think that whole container is like 25 degrees Celsius, but I don't think the gas itself is like at 25. I think it's a close, but it's not. Definitely not D. And then at STP, I think they say 1 mole is 22.4 liters, but I think this isn't exactly 1 mole. I don't know. It has a lot to do with approximation. And then for this, more molecules if it was filled with CO2 rather than N2. I think the molecules would be the exact same. Yeah, it's only that. Hooray! So that's that covered. Any questions? Assume not. Okay. Next, going over the actual midterm, and you can need what grade I got there because I do not care to download this as a PDF. Okay. What the? Why can't I center this? This is wonky. All right. Fill in the circle next to the correct molar mass. I'm not gonna do this like in front of you guys because I assume you guys know how to do it. Just count up whatever's inside and then do it. Largest bond angle, just carbon here. This is trigonal planar, which is 120. That's pretty self-explanatory. There's this one, although you'd think it would be 180 because it's 2, it's not. It's bent because oxygen has 2 electrons. It'd actually be closer to like its electron geometry would be trahedral. And the rest are just not even close. So it's 120 because of all the trigonal planar. What causes aspirin to be a solid at 300 degrees Kelvin? It's all 3. It can hydrogen bond because it has an OH here and acceptors with the oxygen here and here. It has a dipole because this is clearly this is clearly a polar molecule, and it has dispersion because it's a molecule and therefore it must have dispersion. Equally good resonance structures does aspirin have beyond the one above? It has 1 because I think you can move this stuff around. You move this oxygen around and the carbon. Yeah. And then if a dose of aspirin contains 0.0036 moles of aspirin and global aspirin production per year was blah blah. This is literally just dimensional analysis. You should be fine. Also, is this equally good resonance structures? The reason why, if I move this oxygen to say, you can see my mouse, right? Yeah. If I move this oxygen to say over here or over here or here, it wouldn't work because a whole molecule would look different and therefore it'd function differently. If I just move this oxygen here, it's literally the same thing as flipping it upside down. Even though, yes, that is technically similar to an enantiomer and would function differently, I think it's saying equally good as in like it's a resonance. So yeah, that's I assumed that I was doing it. My answer was right. The logic is flawed a little bit, but I think it should be fine. Okay, second. Descending order of van der Waals A constants. Oh my god, I forgot about this van der Waals A thing. So if we look, this is van der Waals, where A is how pressure is modified depending on, I guess this N here. God, it's been a really long time since I did this. I think van der Waals A constant. I remember what it means, but I can't remember it off the top of my head. Yeah, A is attraction and B is the constant for the volume. So for attraction, we're looking at intermolecular forces. So here, this is London dispersion, this is London dispersion. It says H bond's dipole and London dispersion. I say H bond kind of because it has this oxygen that can accept H bonds. It doesn't really have H bond donors. Well, the hydrogens can, but it's not really gonna want to because it's kind of unhappy. And then this thing here, it's a pretty large molecule, so it has bigger London dispersion, and also it has a bigger dipole. So it would probably be this. I don't know why I said probably because I know this is the right answer because I got it graded. Yeah, at 600 degrees Celsius, the total kinetic energy for 1 mole, blah blah, not that 1 kilojoule, blah blah. Assuming standard gas behavior, what is the total kinetic energy in 1 mole of CH3 at 600 degrees Celsius? So pretty much what we did here was we can find the kinetic energy for, well, we can find the kinetic energy for CH3 because at a specific temperature, the kinetic energy of all molecules are going to be the same. It's just their velocities are different. So we know that its kinetic energy is going to be the exact same at 10.9. Which of the following conditions would the ideal gas law be most trustworthy for describing the properties of blah blah blah? So again, remember what we said earlier, which was, I think, was it high temperature that it obeys ideal gases? It's definitely not 0 degrees Celsius because that's way too cold. Same thing with -20. I think it had something to do with high temperatures. Yeah. I just picked this one because it was the highest temperature and it was right. I don't know why they don't give us like reasoning for it here. And they don't tell us. The van der Waals constants for CH3, CH3, blah, blah. How much pressure does the real sample? Just plug that into the equation we saw at the very beginning. What is the strongest type of intermolecular attraction that exists? Did I get this one wrong? Yeah. I said hydrogen bond. I don't think that's right because it technically can't hydrogen bond. So it would probably be dipole dipole. Is that the right answer? Yeah, it's dipole dipole. I overthought it because I thought technically, yes, this thing can hydrogen bond like slightly, but it's not like an actual real hydrogen bond and like attraction. So it's dipole dipole. Moving on. Sodium bicarbonate, commonly known as baking soda, blah blah blah. It is a salt. Fill in the circle next to the correct formula for the cation within. Oh, yeah, the cation positive charge. It's really just the Na because HCO3 is like carbonic acid, I think. Okay, complete this in carbonate. Oh, for this, I literally lost points on this one, I think, because I forgot to add the formal charges onto the individual molecules. I remember the overall charge, but I forgot to add the little formal charges onto the little things. So if I were to do this, I would have to like write on this oxygen that it's like it has a formal charge here and over here because it's non-zero. That's literally all I forgot to do. So if I look here, yeah, incorrect formal charge. Rest in peace. So within bicarbonate, if it's within, it's going to be covalent because it's sharing electrons. If it's saying tween, it's ionic because it's an ion plus the bicarbonate. And then a cake calls for 6 grams. This is just molar mass. So just molar mass and yeah, just molar mass. So 6 divided by molar mass to find moles, and it's that. Baking soda acts as a leavening agent. Blah 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 blah. Write your answer rounded to. This is just unit conversions. So for every mole of NaHCO we add in, we get like a half a mole of CO2 out because of the chemical formula. So we just convert and then do PV-nRT to find out how much gas you get. The carbonate ion, anion, blah blah is present in the Na2. What is the bond order for CO3 2 minus? Wait for each carbon oxygen. Is it not just? It's 4 or 3 because like 1, 2, 3, 4, and then 3 total like bonds to the oxygen. So it's just 4 3 because double bonds count for 2. Yeah, I think that's how I count bond order anyway. How to count bond order? Yeah, total number of bonding pair and divide by total number of bonds. Yeah. So for example, where's an example? This one here. It'd be I don't know why that looks ugly, but it would be for this molecule on the right here. It'd be 1, 2, 3, 4, 5, 6. 6 divided by 3. This whole thing would have a order of 2. I presume this 4, 3 here would be when they had not added the others. Yeah. text. Oh my god, I forgot how long this test was. Okay, for an ideal gas, which of the following results in an increase in the pressure? So again, remember that anything on the right side of the equation are going to be proportional for pressure. So if we double the temperature and the number of molecules, which is just doubling T or doubling N, it would increase P. That's it. If we cut the temperature in half, it would cut pressure in half. If we double temperature and volume, it would do nothing whatsoever. If we doubled the temperature and cut the molecules in half, nothing would happen. If we cut both the volume and the number of molecules in half, nothing would happen. And the largest bond angle in AsCl5, it's 120 here because the symbol, this is trigonal bipyramidal. Because if you look at the periodic table, arsenic has formal charge of 5, and it made 5 bonds. So 1, 2, 3, 4, 5. It's going to have 120 here and 90 there. So the longest would be 120. Molecular of PF3, it's pyramidal because phosphorus has a formal charge of 5. So it'll have a lone pair, which makes it tetrahedral. But that's electron shape. So for molecular shape, we ignore the electron. So that makes it pyramidal. What contains the most polar bond? Again, anything that bonds to that fluorine there would be polar, would have the most polar bond. So that. And then, which gas has the highest average velocity? Remember, velocity, not kinetic energy. We look for the one that's the lightest, which happens to be CH4. Intervals A constants, which are attraction, 2.28, 4.38, and then 5.74, based on which information we have for the highest boiling point. It's GeH4 because it has the highest attraction, which means it's not really going to want to melt. So that's that. And then the best way to explain the previous question, yeah, GeH4 has the largest electron cloud, which means it has a bigger dipole, and therefore it has more intermolecular forces, and therefore would not really want to melt. Number 8. Which of the following is the least likely to form an extent 3D solid with itself? It's F, because fluorine really would rather fill its electron cloud instead of sharing it, because remember, it has 7. So it would much rather make F2 than bond with more, because then its formal charge would be extremely unhappy. So it would probably not want to form an extended 3D solid. Also, we know it's a gas, so it would like being F2 rather than bonding into like F30 billion and like make something like that. We know carbon can definitely make an extended 3D solid. Same thing with silicon and sodium, because sodium metal's a thing. Silicon itself is also a thing. And the graphite in your pens or in your pencils and diamond and graphene are all extended carbon 3D solids. And then for sulfur is sulfur. So I think, yeah. Which of the following is not a valid Lewis structure? I think I put this one because I thought that like something to do with like formal charges and whatever was off with it. Wait, which one was the answer? Wait, hold up. Was it this one? This one, right? Yeah. I think that has to do with like how the oxygen is placed or something. I'm not entirely sure, but I think, yeah, that one's weird. And then looking at the following, which of the following is impossible? Mg has 12 protons. If Mg had 14 protons, it would be a completely different atom. You can add neutrons. That's how you get isotopes. But you cannot change something's proton count, because that will change the very identity of the atom, and we do not want that. Which of the following is unlikely to be true for a solid held together by ionic bonding? Ionic bonding will mean that it probably dissolves water. It will probably contain multiple elements, and it will also probably be brittle, as seen in our little NaCl, because solid is not solid, salt is like a crystal, so it's probably also going to be brittle, just like how sucrose was. So we presume conduct electricity, because them on their own, I think, can't conduct electricity, but when they're dropped in water, then they can conduct electricity, because then you have the individual ions floating around. But for now, it can't do it. Where's the missing formal charge on 9? Yeah. So what's wrong with it here I didn't notice is that you see how this thing has a little plus on it? This thing has a minus. If you look over here, this oxygen, it's not happy in its little formal charge, so you're gonna have to slap that little thing on it, I think. Yeah. Alrighty, that's that. I have, I think, an hour before my intramural game, so I need to go practice for that, because otherwise I'm going to throw, and it is playoffs, and I do not want to throw. Can I go back to 5? 5 as in, like, this one? This one? CH4 has the higher average velocity because it's the lightest, I think. Okay, I think I'm almost out. No, I'm definitely out of water. Okay, well, that's module 1. Hopefully everything was covered. It's extremely simple. I think the hardest bit was like understanding formal charges and also remembering exactly what was part of the van der Waals constants or whatever. But it's literally just an equation as to understanding what's what. So just a quick refresher like this will probably help. I feel like the worst module to review will probably be tomorrow, which is acids and bases. But thankfully, that is my specialty because I had to explain it to so many goddamn people. I remember it entirely. So I will go over the homework for that section probably, and then the actual midterm that we did. Yeah. So tomorrow I'll go over, I think number 15 and 16 it was on achieve, because those are the ones that everybody hated and I explained 10 billion times. Let me go and look at it again. I need to remember which module it was. Or which one it was. What is it, like homework 5 or 6? I'll probably remember it when I see it, because that thing made me want to cry, but is it this one? Is it the one after? There's a one after. Which one was it? I don't remember. Can you help me? Where was acids and bases? I think it was after. It was after this one. So 7 was it? Is this titrations? Titrations I'm so good at now. Yes, it's these. Everybody hated these, and I had to explain it so many times. So it's this. That is homework. What homework is this? 7. I will explain number 5 and 5 or 6 and 7 here because nobody knew how to do it, because this is basically titration. So this and the, where is it? If I go back, yes, I'm exposing my grades. Oh my, this and this. Okay, I got 3 wrong, and then like each question was worth so many points because I overthought. This one, I'm literally so pissed at myself that I got this one wrong. I input my numbers wrong in my calculator. I had to answer the first time. Look, I freaking bubbled that shit in, and I erased it, and I'm so sad. And this one, that one's a bummer, and this one is also a bummer. It was B. It was this one. I had it right, and then I overthought it. Okay, I will see you all tomorrow. Well, not really see you, but you will see me tomorrow. Okay, goodbye.